Hello class, this is CSE-5250, sections 2 and 60, week 10, spring 2025. Alright, so now's the time that I hand you the instructions for your second benchmarking project. So, if you've been following along with the programming assignments for OpenMP, by now you should have several different versions of the trapezoidal rule program. 4 different versions in just the first programming assignment, and then the second one, 2 more that uses the parallel for directive. So the first one that you wrote was all the way back in programming assignment 1, and this is it right here. We were working under the same mindset as we were with pthreads, where we wrote a multi-threaded function that is, or rather, we didn't write a multi-threaded function. Rather, we wrote a function that we called by multiple threads. For each thread, we had to calculate a separate starting and stopping location. But the beauty of OpenMP is we didn't even need to do all of this. All of that work of figuring it out how to divide the work among all our threads is done for us. So we could have just started with a single-threaded trapezoid rule program, shown here. And by the end of the second programming assignment, we would have ended up with this. This is the trapezoidal rule program that uses a parallel for loop. So the parallel for loop does all the work of calculating a stopping and starting point for each thread. Actually, it doesn't even do it like that. Rather, it divides the work behind the scenes. So, instead of writing all this code where we had to find out a local starting and local stopping point and the local number of loop iterations, we don't even need to write any of that. We just slap in a pragma OMP parallel for, and that's it. We would have to, however, add some other stuff to it, such as, in this case, a reduction clause that specifies, hey, we're adding to this approx variable repeatedly, so we're just gonna declare that to be a reduction variable and reduction operation of addition. That is to obviate the need of writing a critical section. And then this private x and my rank, that's to make sure that any changes to those variables, because these are shared variables, we want to make sure that every thread has its own private copy. That way, if one thread changes the value of my rank, it only changes the value for its own instance of my rank. So we wouldn't get race conditions. In fact, these two are related to preventing race conditions. Reduction clause obviates the need to add a critical section. Private clause also does that to an extent, but mainly it obviates the need of having to redeclare variables from outside the for loop to inside the for loop. So yeah, we could just write something like this, where we could write something like this. But the point of the private clause is so we don't have to do that. The point of the reduction clause is so we don't have to add in a critical section on our own. The point of all of this stuff is to minimize the amount of code we need to rewrite. And that's the beauty of OpenMP. If you have a program that you have already verified works on a single CPU, and you have determined that there are no loop carry dependencies where the result of the previous loop iteration affects the result of the next loop iteration, then you can just add a parallel for directive plus a few other clauses just in case, and turn the whole loop into a parallel for loop. How neat is that? Oh, by the way, I want to show you what happens if you try to parallelize a for loop you shouldn't parallelize. So this was one of your this was part of one of your programming assignments where I had you try to write a program that would find Fibonacci numbers. And I do understand that there are ways of calculating Fibonacci numbers that don't require finding the previous Fibonacci numbers before that. But we are going to run with the idea that it takes finding the previous Fibonacci numbers to find the next one. So this is to demonstrate a pitfall with trying to parallelize for loops. So I'll be right back and I'm going to write that Fibonacci program really quick. Okay, I went ahead and wrote the program really quick. So I'm going to compile it now to see if it works. So G CC -G -wall -f OpenMP -o. I call it fib.c. So fib.c. Okay, so there are a few things I have to address. So yeah. Okay, so that is just an unused variable. That's a non-issue because I'm gonna use that in a little bit. There are a few things I have to address here, so I'm gonna double check my data types right now. Be right back. Okay, looks like I forgot some square brackets here. Let's try that again. Okay, so the only problem now is the fact that I have a unused variable, and while that gives you compiler warnings, it's there to help you write cleaner code. It's saying to me, hey, you probably don't need this variable, but the problem is I actually need that variable in the next step. So I'm gonna ignore that warning and I'm gonna run the program. I'm gonna run the program with, actually no. I'm gonna comment out that whole line because nothing about this program requires me to pass on a thread count yet. Because I don't even have a parallel for directive in here. So I'll recompile the program, and all the OpenMP stuff is gonna be redundant and ignored. I'm gonna run the program, fib, and there we go. We have Fibonacci numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, so on and so forth. So the next number in the sequence is going to be 1.618 ... times larger than the previous. So that's how you can calculate the next Fibonacci number based on the previous one. So if you do that, take 1 and multiply by 1.618. You're gonna get 1.618, but you'd have to round up to 2. And then you take 2 times 1.618, then round it to get 3. That's how you would do it. That's how you would calculate the next Fibonacci number without having to calculate the previous ones. But the thing is, you can take random numbers, multiply it by 1.618, and get another number that's 1.618 times larger. So 23 would be a number that you could just multiply by 1.618, get the next number in the sequence, even though that's not anywhere in the sequence of numbers. There is a variant of the Fibonacci numbers called the Lucas numbers, where you screw it up with the initial numbers. Like, instead of like 1, 1, 2, it's like 1, 2, 1 or something. But it still converges to the Fibonacci sequence, in that they still grow at a ratio of like 1.618 times larger than the previous. Anyway, enough math talk. Let's see what happens if we try to parallelize it. So, what part 0 of the previous programming assignment is meant to demonstrate is the pitfalls of trying to parallelize a for loop that shouldn't be parallelized. So, I'm going to uncomment out this thread count, and then I'm going to add in a parallel for directive. So, pragma OMP parallel for thread count, no threads, thread count. There we go. Now I need to pass in a command line argument. I'm going to recompile that program. I'm going to run the program again. But if I do that, I get a segmentation fault. That's because I didn't pass in a thread. If I pass in 1, nothing bad happens. If I run it multiple times in a row, still nothing bad happens. And that's because with one thread, there's nothing to compete with. You can't get race conditions with just one thread. You need 2 threads at least to get a race condition, because one thread would interfere with the operations of the other. So if I use 2 threads, okay, it worked fine that time. But if I do it again and again, okay, nothing seems to be bad happening. What if I do it again with 3? Oh, we're getting something. Now, if I do it again with 4, it starts to get worse. If I run the program with 4 threads, one thread is going to have to calculate the first set of Fibonacci numbers, and then the next thread is going to calculate the next batch of Fibonacci numbers after that. The next thread calculates the next Fibonacci numbers after that, and the next thread calculates the next Fibonacci numbers after that. The problem is, those 3 threads have to calculate the next batches of Fibonacci numbers. They have to do it in sequence, but we're forcing it to be parallel, so the threads are forced to add whatever was in memory already. So that could be whatever was in memory. Who knows what's in memory at that moment? So the threads are just adding literally whatever was in memory, and now we get nonsensical numbers. That's why a lot of these are negative, because the threads just jumped the gun. The threads jumped the gun, and now they're just adding whatever was in memory. We can make this worse too. So check this out. So can we parallelize printing the Fibonacci numbers? I'm gonna remove this pragma and move the pragma over here. So it's going to calculate the Fibonacci numbers normally, but it's gonna try to print them out in parallel. Here's the pitfall in trying to do that. Okay, recompile, and oh, wrong line. There we go. Try that again. Clear. And now I'm gonna run the Fibonacci program with 1 thread. Again, with 1 thread, there should be no competition because there's nothing to compete with. If I do it with 2 threads, okay, looks fine there. But you see the problem now? We're getting the Fibonacci numbers, but look, 1, 1, 2, 3, 5, 8, 13. How did it jump to 10,000? And then 100, and then 17,000, and then 21, 24, 55. That's the problem. Some for loops that could be parallelized, even if it looks like a for loop could be parallelized because it's of canonical form, there might be loop carry dependencies that would suggest, hey, maybe you shouldn't parallelize this at all. But in the case of printing out the Fibonacci numbers, there is no loop carry dependency, but we are expected to print all of these numbers in the correct order. And if we don't do that, we get this, where, yeah, we do print out the Fibonacci numbers, but they're all in the wrong order. Oops! I'm gonna do it again. Let's do 6 threads. And they are really in the wrong order now. So, yeah, this is a pitfall with trying to parallelize for loops. Even if it looks like it's canonical form, some for loops just cannot be parallelized. Well, should not be parallelized. Not because anything bad will happen, but because you'll get the wrong output. There is a song where someone tried to get, in the bridge of the song, someone tried to get an edgy 13 tattoo, but the tattoo parlor screwed up and they gave him a 31 tattoo. I like to think that that happened because of shenanigans like this, where the numbers were just mixed up. and they are mixed up here. So anyway, that is the point in trying out the Fibonacci numbers program. Really, if we want to truly parallelize it, we would need to feed in, say, the number 13, and it would then calculate the 13th Fibonacci number from there. So when I talked about multiplying the previous number by 1.618, even that would not be enough because, as I mentioned, you could just feed in any number that isn't within the sequence of Fibonacci numbers and still get a sequence of numbers whose growth rate is like still the golden ratio. So, enough of that, let's look into benchmarking our OpenMP project. So, it's going to be much the same as it was with the P-Charts program. For part 0, calculate the number of CPUs your system has. If you are using the same exact computer from the P-Charts project, you can just safely skip this step. On the other hand, I tinkered with the settings of my virtual machine, and I was able to allocate 6 CPU cores to my VM. Someone told me I could over-provision CPUs to my virtual machine, but I have yet to figure out how to do that. So, yeah, I have yet to figure out how to do that, so I'm just going to leave it at the 6 CPU cores for now. That means if I run multi-threaded programs on my virtual machine, it means I now have an extra 2 cores from the last time I tried to benchmark. So, I'm going to clear this console, and let's look at those instructions. Right, so part 0, just determine how many CPUs your system has. Part 1, you're going to create a table, and again, these are all sample values here. Create a table as follows: 1, 2, 4, 8, 16 threads. Replace these values with your actual times. Run your program with 1 thread and 1 million terms using the command time, program, 1, and then 1 million. I'm going to have to modify that because the trapezoid rule program has 2 steps with entering your numbers. So, actually need to close that. So, let's go and investigate the Trap6 program here. So, if you have done all the programming assignments to date, you will likely have this program here. So, this was a single-threaded trapezoid rule program, but we added a parallel for directive to turn the code within the trap function parallel. So within the trap function, one thread calls the trap function, and within that function call, a team of threads is created, runs the parallel for loop, and then joins back when the for loop finishes. So no more having to call the same function by multiple threads. We have one thread call one function, and within that function call, a team of threads is created, runs the code, and joins back together. So here's that modification I'm talking about. So this is the Trap6 program. I'm going to open this in terminal, and here's the problem. /Trap6. Okay, it's not the fact that I got a segfault. I'm gonna run this with 6 threads because I can. And that's the extra step. Enter the starting and ending points A, B, and the number of trapezoids N. So if I do 0, 10, 10,000, we're gonna calculate all these X values, and then the program is gonna calculate what the area under the curve is, which, as we have seen many times before, should be something on the order of 333 and 1/3. So we're gonna have to make some changes to our code. So instead of having, this is for the ease of being able to run the program repeatedly, because as you can tell, I cannot re-enter the same values as I did. I can't re-enter the same values that I did. So I can't use the up arrow key. But I want to use the up arrow key just for the ease of running the same program repeatedly. Clear? So here are the changes I'm going to make. I'm going to save this as trap 7. Save that. I'm going to then comment out those values. Yeah, I'm going to comment out lines 25 and 26 in here, where the user is prompted to enter the starting and ending points. Instead, we're going to parse the starting and ending points from the command line arguments. So here's how it works. The first argument we type in, that's the thread count. The second argument we pass in, that's the starting point A. The next one after that is going to be B, and the next one after that, that's going to be the number of trapezoids. So here's how that works. A equals str toll, and I want to double check whether this can parse a floating point value. Okay, so str toll will not work. Str toll parses, in this case, it's going to parse a string into a long integer, but I want double. So that would be rather str_tod. So this will parse our command line argument that's supposed to be a floating point variable, in this case it's a double, into, well, a double. So str_tod argv2 null, and hold on, let me double check the arguments to be passed in here. So okay, so here is what we do. We don't use str_toll for our floating point values, rather we use str_tod for that. So for the first argument, that's going to be the command line argument that we passed in. So the first thing that we pass in, well, the 0th thing that we passed in, that's the name of the program. The first thing, so argv0 is the name of the program, argv1, that's our thread count, argv2, that's our starting point, that's our value A. argv3, that's our ending point, and argv4, that is the number of trapezoids. So for A and B, we use str_tod to parse those as floating point values. We're going to pass in null for the second argument for str_tod. There isn't anything that we have to pass in for a third argument because there is no third argument. That is only for str_toll, where we parse our value as a base 10 value. So let me just comment this to make sure we're all on the right page. So argv2 is the left endpoint, argv3 is the right endpoint, argv4 is the number of trapezoids. So now, instead of running the program and then entering those values A, B, and N, we now pass them all as command line arguments. So I'm going to recompile the program, and now I'm going to run it like this, where we're going to do one thread, and I'm going to do it from endpoint 0 to 10, and I'm going to do it with 10,000 trapezoids. So now we get this. The area under the curve is 333.23 whatever. However, I want to comment out this line where it's printing out what each thread is calculating. So I'm going to go back into trap 7, and I'm going to comment out this line where it says thread%d of d has calculated x. I don't need that anymore. If anything, it's going to get in the way. So I'm going to now recompile the program. Okay, my rank is set, but it's not used. And that's because, well, that's literally what's going on. We're not using my rank anymore. But we're gonna ignore that warning for our purposes and just run the program as this. So now, this is what I wanted to get to. Instead of running the program and doing 2 rounds of entering values, we only do 1 round of entering values when we run the program. So /trap7 1 0 10 10,000. That means run the program with 1 thread, have the starting endpoint be 0, have the ending endpoint be 10, and divide the area under the curve into 10,000 trapezoids. If I run that, I get the area 333. So this is a much faster way of calculating the area under the curve. Or at least one that is conducive to running the program repeatedly. Because we want to get benchmarks. For us to get our benchmarks, let's do this. We're going to add back our time command to that. So it's going to get us runtimes for our program. So the area under the curve is 323.2 something or other. We get times for how long the process ran for. So this is on the order of milliseconds because we divided the area under the curve into not a lot of trapezoids. If I instead did this with, say, a lot more trapezoids, now it's really struggling, but I'm concerned that I probably gave it too many zeros, so let's do that again. So let's do 1 million trapezoids for now. So that ran in about 15 milliseconds. I'm using the real time here. If I clear that. So real time 15 milliseconds. Now if I try that again, and I did 6 threads, I do get a speed up. So that is how we benchmark our program. So in fact, I'm gonna have to rewrite the instructions for the pthreads project so that it's clear what we need to do. So give me a minute. Right, so I've now clarified the instructions for your OpenMP benchmarking project. So part 0A is how many CPU cores does your system have? Part 0B is doing those rewrites. You don't have to submit this, by the way. Really the main point is to submit your benchmarking results. So I've rewritten the instructions to be clear on what to benchmark and how to benchmark. So begin running the program with 1 thread, endpoints 0 and 10, and 1 million terms using the following command here. So 0 and 10, okay, so this 0 and 10, the second and third command line arguments, those will remain fixed throughout all of our experiments. The only things to be changed are the first and fourth arguments. So the first one is the thread count, and the last one is the number of trapezoids. We're gonna, much like with the pi estimating program, we're going to change the thread count while keeping the number of trapezoids fixed. Then we're gonna increase the thread count. No, we're gonna increase the thread count and then do it again. Once we get to the 16 thread case, we're going to reset the thread count to 1, and then we're going to increase the number of trapezoids from 1 million to 10 million. Then we're going to benchmark again. So we're going to fill this table 1 row at a time, much like how we did with the pi estimating program. And then much like with the pthreads project, with the pi estimating program from that, we are going to calculate a table of speedups. So how much faster was the 2-thread case over the 1-thread case? How much faster was the 4-thread case over the 1-thread case? How much faster was the 8-thread case over the 1-thread case? So how much faster did these programs ran with more and more threads for the same number of trapezoids? And then finally, you're going to answer the following questions. So, where do you think the sweet spot is for thread count? Where do you think the sweet spot is for workload size? Do you think this was a worthwhile speed up by the number of seconds saved? How about proportionally? At what point did you stop seeing any speed improvements? How do you compare your experience with programming with OpenMP compared to pthreads? So that's a new question that you're going to be answering. How was it like to program with OpenMP versus pthreads? Was it any easier or different? And again, you have the 6th optional question. So this is 75 points worth of questions here. The speed up table is 30 points. Benchmark table is 30 points. So those are your deliverables. So speed up, the table of benchmarks is 30 points, the table of speedups is 30 points, and then the results is 15 points. So yeah, that's it. So this is going to be your pthreads project. No, your OpenMP project. It says pthreads project up here when it should say OpenMP project. So those are the instructions for your second benchmarking program. So the fact that it's spring break, or it's going to be spring break by the time you get to this, is going to be a little bit of an issue, and that's why I intend to have the due date for this program to be on the beginning of week 12. So week 12 is going to be, let's say, the Monday of week 12. So that's going to be the tentative due date for your second benchmarking program. And then a few weeks from that, you'll have your third and final program, which is a benchmarking program. It's a benchmarking project with MPI. So MPI is going to be a little bit different from OpenMP and pthreads. Okay? So if you have any questions about this project, definitely feel free to let me know, and then we can discuss it over if you have any questions to be clarified, or if you need help with trying to get your program to run. So, as I said, the point of parallel programming is to make up for the fact that Moore's law, as it's used to describe clock speeds, hasn't really kept up. We can't make our CPUs any faster if we're going by clock speed alone. We can employ tricks to get it, and to get it faster, such as pipelining, but even that has its limitations. So we gotta go with making multi-core CPUs, and that requires rewriting our programs wherever we can so that they can leverage the multiple CPU cores on your computer. And that's before we even talk about, say, programming on a GPU. Although I don't assign you any work on that, I guess it is worth a discussion as well. Oh, programming on a GPU. Maybe a little bit later I might get to talking about that. So anyway, these are the instructions for your OpenMP benchmarking project. How many cores are on your system? Rewrite your trapezoidal rule program once more. You do not need to submit this. Providing a table of benchmarks, providing a table of speedups, and then answering the following questions here. Where do you think the sweet spot is for thread count? Where do you think the sweet spot is for workload size? The number of trapezoids. Was there a worthwhile speedup by the number of seconds saved, or versus proportionally? At what point did you stop seeing any speed improvements? How would you compare your experience with programming with OpenMP compared to pthreads? Was one easier compared to the other? let me just make sure that all is good with the instructions. So, give me a minute. Okay, so that's gonna be it for the instructions on OpenMP. The project will be assigned to you now, but the due date will be about 2 weeks from now, a little over 2 weeks from now. And that's to account for the fact that we have spring break upcoming. You might already have plans, but I want to give these instructions to you now, so that way, if you'd like to get it done and dusted, you can just speedrun through the project and then have it done and dusted. Okay? Alright. So, this will be made available on Canvas, and as I said, the project itself, Project 2, will be due on the Monday of week 12, with the 2-day grace period as per usual. Remember, the usual grace period of 1 week after the due date does not apply to the projects, rather it's a 2-day grace period, okay? Okay, right. And as I said, if you have any questions, let me know, and we can talk it over, right? That's gonna be it from me. Have a good spring break, and we'll catch up a week or so from now, where we will start talking about MPI, alright? Take care, have a great spring break, and I'll see you on the other side of spring break, week 11. Right? Take care, and goodbye. Have a good one.